So good day to you. My name is Professor Martyn McLachlan from the Department of Materials at Imperial College London. In my presentation today, I'd like to discuss with you some recent work on understanding the structure, composition and performance relationships that exist within perovskite solar cells. Actually, the presentation today, I'd like to tell a story of our work over the last 4 or 5 years. And in doing so, highlight the contribution of a number of exceptionally talented graduate students, many of whom have finished their studies during the recent pandemic, and thus have been unable to themselves get out and speak about their work. So here I'd like to really highlight some exceptional work from those students listed, as well as highlight a number of collaborations that we've been lucky enough to have as a research group. So first and foremost with the group of Professor James Durrant at Imperial College, and in the work towards the end of this, the aerosol assisted solvent treatment, that with the Briscoe group at Queen Mary University of London. So really to begin, I want to just give an introduction to perovskites, that those that perhaps aren't familiar. And the classical perovskite structure here is this mineral structure that adopts this ABX3 formation of cations and anions, and the name is derived from the first known or the first discovered perovskite, calcium titanate, and I show the structure here. Over the last decade or so, metal halide perovskites have emerged as materials that have exceptional optoelectronic properties that have found use in a number of device applications. Today I'm going to just focus on the photovoltaic aspects. Again, they adopt a similar structure to calcium titanate. However, we have the introduction on the A site of the cage here, typically a organic-based species, methylammonium or formidinium. Now increasingly cesium and other large cations being substituted there. On the B site, typically a metal, classically lead, and I'll speak only about lead containing materials today. Tin and others are being explored, and then a halogen on the X site. So again, typically chlorine, bromine or iodine being used. Really, this gives rise to a number of complex structures that can be prepared, and the workhorse material here is perhaps the simplest. So on the A site, methylammonium, on the B site, lead, and on the X site, iodine. This material, methylammonium lead iodide, or MAPE, as I may abbreviate it during the presentation today, was the first reported and perhaps has been the most widely studied of materials. Given access to this number of lattice sites and the number of complex compositions, then actually the materials that we see now tend to be rather more complex. So the so-called triple cation structures that have been developed for a variety of reasons, some of which I'll discuss, and again with these mixed halides in addition. So I'll begin by speaking about MAPE, but in the first case, I just want to highlight, I think, the opportunities and challenges that exist with perovskites. So again, this compositional variation has often been driven by the desire to have broad tunable absorptions. The materials have intrinsically long carrier and charge carrier diffusion lengths and are intrinsically solution processable, thus access to low temperature, large area film deposition is possible. And I'm sort of introducing a term of molecular gastronomy, I think, given just the large number of ingredients, if you like, that we can put together in order to prepare a perovskite. All of these factors combined, and I think combined with the relative ease of fabrication, have given rise to a tremendous number of academic papers, particularly over the last decade, where we see this steadily increasing and relentless number of papers that seem to persist every year. If we take a 5-day working week, then the output of 2021 is around 7 papers a year that have both perovskite and photovoltaic in their title. There are many others that don't have these keywords, and many others that aren't used in the photovoltaic arena. The impact of the academic output however, has been significant. And here we're looking at the photovoltaic cell efficiency chart, just one section of this emerging PV that's produced by the National Renewable Energy Laboratory in the United States. And again, the perovskite cells indicated here with the red circles with the yellow infill. Again, what we can see is this really remarkable increase in measured device performance conversion of power conversion efficiency from the first recorded cells around the mid 2010s, rising up now to champion performances that actually exceed 25, pushing 26% power conversion efficiency. In addition to academic curiosity, it's pleasing to see that the significant volume of intellectual property that's been generated in the photovoltaic arena. And again, we see here a nice mix of both industrial and academic partners, which I think highlights the potential future for these materials as they begin to be translated into a commercial reality. There are some disadvantages, of course, and those familiar with the area will know this very well. We tend to have often intrinsic instability when the active materials, the perovskites, are exposed to oxygen, moisture, even in some cases light, and they may undergo a crystalline phase change in what would be considered a normal operating temperature. We have issues of both ion migration and defect migration, and of course the cells containing lead, a toxic material, are just some of the challenges that present themselves. Again, the large number of papers has perhaps also been supported by the relative ease of formation. So here we simply show what we do in terms of making a film rather simply. So we take our two precursor materials. This is methyl ammonium lead iodide, this is lead iodide. We mix these together in separate or the same solvents, and ultimately, as I said, at low temperatures, so less than around 150 degrees C, we can form this crystalline methyl ammonium lead iodide. The steps that are involved in this are actually a little bit more complex. It's not a one-step process, and we can split this up into, I think, 3 to 4 key stages. So in the first, we think about the mixing and the compositional control of our recipe, if you like. So the compositional control of and solvent selection that we use for depositing a film. We then deposit a film here, I'm showing via spin coating, and then we have 2 stages of processing that occurs in the wet, the non-solidified, non-crystalline film, and that occurs in the film post deposition once the film has been completely dried. And what I want to do today is go through each of these and show a little bit of where we can get control and ultimately enhance performance. Intrinsically, materials with low formation energies will typically also have low decomposition energies, and here we can see very nicely on the right hand side the film of methyl ammonium lead iodide, which will look to many to be analogous to a piece of silicon wafer, for example. So we see this dark grey black material that is very highly reflective, and on exposure to any of the factors I mentioned previously, this decomposes to here this yellow material, which is one of the precursors, which is lead iodide. This is an interesting process because, again, as we undergo this decomposition, we can monitor it and understand in more detail about structural stability, and again, thinking about the influence of compositional control on stability. And we can do that a number of ways. So here we see optical data, and we see structural data here through scattering and diffraction measurements, or even simple measurements of current voltage characteristics as a function of time. And often these would be correlated. We would be measuring device performance with some structural or optical probes to understand the phases formed and the rate at which they're formed. So in the first topic today, I said I wanted to speak about crystallinity and compositional control. So this is phase 1, if you like, of the film formation process. And again, our standard recipe, we would mix together in equimolar ratios our 2 precursors, methyl ammonium lead iodide and lead iodide. What we started to think about was the influence of the ratio of these 2 materials in introducing a slight excess of methyl ammonium iodide. So again, we can think of coming up with some terms for these. So from the equimolar to the slightly deficient, and then the slightly rich MEIs, all the way up to 10% in principle, 10% stoichiometric excess. The films that are prepared using these compositions optically show no variation at all. So either by naked eye or more accurately by ultraviolet visible spectroscopy here, we can see it very comparable absorption onsets regardless of the excess of methyl ammonium iodide. In contrast, when we look at the here we see scanning electron microscope images of the surface morphology of the films, and we can start to see quite clearly that we see an increase, very gradual increase in grain size as we increase the methyl ammonium lead iodide concentration. The result of this we can quantify more accurately using, in this case, X-ray diffraction measurements, and we see here from the reference material shown in red that as we begin to increase the concentration of methyl ammonium iodide, then we see a sharp increase in peak intensity. We can do this more quantitatively by looking at the integrated peak areas, and that very clearly shows that we have a significant increase in crystallinity as we continue to increase the content of methyl ammonium lead iodide. What is important, and here I can just summarize some device performance parameters. So what is important is, despite the previous data showing this continuing increase in crystallite size, here we see the largest grains down with the 10% methyl ammonium lead iodide. The corresponding films actually perform relatively poorly, and in fact here they perform worse than the reference cells. So again, the idea of roughness and coarsening have a detrimental effect. The champion devices here are produced with an excess of around 5%, and we can see on the right-hand side that that's predominantly driven by this increase in open circuit voltage, and that's a parameter that I'll refer back to throughout the presentation today. Again, the excess of methyl ammonium iodide, in this case, providing additional halogen that we believe compensates for halide vacancies within the crystalline structure that manifests itself in an increase in open circuit voltage. So thinking then about perhaps the second step of the processing and the influence that it can have on device performance. So here we have a little schematic illustration that shows the stepwise formation of films from a wet mixing here. Here we carry out what is called an anti-solvent dripping. So in the wet solution, we add a solvent in which the perovskite is insoluble, it precipitates out, and we form this intermediate phase that would normally then require some additional thermal annealing in order to exit the residual solvent and completely crystallize the film. Here we modified the processing just very simply. So we would normally have in the bottom step here in a conventional processing, we would carry out a thermal annealing. We would then put an electron transport layer or a whole transport layer depending on the device configuration. Here it's a fullerene based layer that acts as an electron transport layer. So we would sequentially dry, then deposit our fullerene layer, and then complete the device. In this case, we simply inserted the fullerene layer, the PCBM in this case, prior to the annealing of the film, and studied the influence of having a PCBM capping layer versus the normal conventional processing where it would be absent. Cross-sectional, in this case, transmission electron microscope images revealed really marked differences between the films that were processed via the conventional and the co-annealing route with PCBM. I superimposed across the film here a dashed line that really splits the film up into two layers. So this light grey area here is the methyl ammonium lead iodide, and we can see a large granular structure. But within these grains and running across approximately the top half of the film, we can see the presence of a large number of these dark spots. We see similar sort of dark or voids here that exist here. These represent the grain boundaries that exist between adjacent grains. When we look at the films, however, that are co-annealed, we generally see these features as being absent. And this is something that we probed and began to look at the structure of the methyl ammonium lead iodide. So what I can see here at the bottom interface in the region that appears to be defect-free, I see highly crystalline regions of the methyl ammonium iodide that are interfaced with this material P.PSS, which is the electronic hole transport layer. The region here, which appears to contain these dark spots, we can identify a number of regions of crystallinity, with a variety of crystalline orientations seen, a number of small crystallites, and in fact a number of poles or voids that appear to be present in this upper region. In the films that are co-annealed, actually we see that we have an absence of these, and we have a real highly crystalline film of the photoactive methyl ammonium lead iodide that exists between both electrodes. And again, we can quantify that further. So here we look at the same films, and we look at this lower interface where we saw that the lack of defects. And here what we can see is electron diffraction from this region that exists in the lower half of the film at that P.PSS interface. But we see a lack of that diffraction, therefore a lack of that orientation, lack of crystallinity in the upper half of the film. And when we contrast that with the films that have been co-annealed, then what we see in the diffraction data here are the presence of, if you like, crystalline coherent orientation between the hole and electron transport layer. And again, here adjacent, a small amount of drift in the microscope here, but adjacent to that, we can see again a grain with, in fact, the same orientation. And I've tried to illustrate that a little bit with the schematic illustration that I've shown to the right-hand side. So again, the impact that what we can see that has happened here is that the co-annealing has effectively slowed down the solvent evaporation during film drying and film formation, that has resulted in the formation of more crystalline films with significantly lower defect densities. And we can quantify the crystallinity by using X-ray diffraction as before, but perhaps more remarkable is the impact in all measured device parameters when we compare those that are conventionally processed, shown in red, and the far superior devices that are prepared here, shown in blue. So again, just working with the methyl ammonium iodide, by thinking about the structural properties here, we can afford significant improvements in device performance. The second thread here is thinking about additive engineering. Okay, so in this case, and previously I mentioned that the presence of defects that exist, so point defects that exist within the perovskite films, and those that we know persist are typically the halide vacancies. The species shown here are naturally occurring, they're amino acids, and it's known that the Lewis base nature of the amine can have a positive influence on halide vacancies. These materials are Zwitter ions, so they carry both a negative and positive charge at either end of the molecule. Therefore, we're able to have this dual benefit in being able to passivate positive and negatively charged point defects that exist within the structure. So here we wanted to investigate the influence of chain length on these dual aspect materials, with AVA being something that had been reported quite some time ago as a processing additive. The Gratzel group reported this in 2014 in mesoporous cells, and our concern was that the chain length here was perhaps too long, and the passivating effect of the N groups was being negated by the insulating nature of the chain. So again, some quick optimization here. So thinking about the concentrations of amino acids, and we explored a large parameter space. Just with the 1 volume percent of amino acid additive, we can see very clearly that the red trace here follows the black trace very nicely, and then we see this systematic reduction in the GSC, the short circuit current density, as the chain length of the amino acid increases from 2 to 3 to 4, and in fact more so when we increase the concentration of the amino acids. So again, we see an optimum we see an optimum at around 1%, and we see this also for the shortest carbon chain, glycine, which is that which we'll go on to speak about. Again, thinking about crystallinity and referring back to the previous work, we see an increase in crystallite size till we get to the 1 carbon. And then we see this rather large reduction in crystallite size as we progress. So again, somewhat consistent with our previous studies, with the additional effect, hopefully, of some defect passivation brought about by the functionality of the molecules. Surprisingly, when we compare the pristine, i.e. the amino acid free in the 1 carbon cell, which was the best performing, we don't see a significant amount of improvement. However, okay, we see about a 0.5% improvement in per conversion efficiency, and therefore the question perhaps exists as to, you know, is it beneficial to add such an additional step and increase the complexity of the system to achieve comparable performances? We perhaps answer that in terms of the stability of the devices. So again, here we look at fresh devices on the left-hand side and aged devices on the right. The reference cell indicated by R here, we can see very clearly is different in color. You'll recall I said this yellow color originates from the lead iodide. It's a degradation product, and we can see here just with films that are left in ambient conditions that I'll just look at the reference cell here. So this is a 110 diffraction peak at around 14 degrees. This belongs to the methyl ammonium lead iodide, the photoactive material. And here what we can see is the introduction of an additional peak associated with lead iodide, i.e. the degradation product, such that after only 3 hours of exposure to oxygen and moisture in the lab, the films have fully degraded. Not the case, in fact, where we have any of the additives. We see something of an insensitivity to chain length in that case. So perhaps here, in addition to the subtle improvements in device performance, justification in terms of stability for adding the amino acids. And this tracks further when we look at device stability in nitrogen and air. So on the left here, we're looking just at perovskite films. On the right of devices, and we can see that we consistently have improved lifetime with the addition of the amino acid additive. Using structural studies, so here looking at secondary ion mass spectrometry, we can confirm the presence of the additive within the near surface layers. So these are static SIMS measurements, so we can confirm the presence of glycine and the AVA conclusively near the surface. And in fact, an additional benefit that's conferred, so here we have 2 sets of devices, additive free and those containing glycine. This is, again, we're looking now at dynamic SIMS, so we're profiling, depth profiling into the sample, and in this region here, highlighted by the circle, this is us moving through the PCBM, our electron transport layer, which is fullerene, so carbon rich. So we see this high carbon profile, which we'd anticipate, but here we see this rather large increase in iodide concentration after 250 hours of device operation, associated with diffusion of iodide out of the active layer and into the electrode. This is something that's well known as a degradation mechanism, but interestingly is absent in the presence of the amino acid, which appears to be acting as a barrier to diffusion. Again, we see similar with additional additives. Again, an additive here, NMA, that's been used extensively in the perovskite LED literature. Again, we see a very similar improvement in device performance to an extent. We optimize the maximum PCE. We see a sharp drop off in power conversion efficiency, which here we can see is very closely correlated with a reduction in current. So NMA it was more interesting because we have this conjugated species. So the question was raised as to whether we could increase the concentration relative to those amino acids and further enhance defect passivation without the reduction of photocurrent, which obviously in this case isn't possible. Thinking then about completing this and thinking about the structures that we present. So here we look at additive free films in cross section, and we begin to see these polycrystalline structures across the film thickness, in addition to those that we see on the surface. What we can see using the NMA additive is that we then have this enhancement in grain size, both laterally across the film surface, but also through the thickness of the film, where we see these single grains rather than stacked grains. Actually, to achieve this, however, we really had to think about the process, and here rather the dry processing. So with the additive and the use of just a straightforward thermal anneal, we see poor device performance. To achieve the superior device performance that we show at the bottom here, it was necessary to introduce a small amount of subsequent solvent annealing after the thermal anneal, so exposing the material to a solvent vapor and improving ultimately the microstructure that then gives us this improvement in device performance. So in this case, stabilized performance is power conversion efficiencies of just over 20% PCE. So to finish, just in the last couple of moments, I'd like to bring all this together and think about not just the role of additives, but how we can control composition, and then ultimately, as I've just shown, the from morphology that results from solvent annealing. So rather than an uncontrolled solvent annealing, that we developed a CVD-based route where we have a heated substrate holder, a heated graphite block, and into this we introduce a mist of solvent that flows in a laminar nature near to the surface region and results in what is referred to as a solvent annealing. So films don't dissolve, but they interact gently with the solvent, and we get this structural rearrangement that occurs. So this is the work that we developed with very close collaboration with, as I said, the Bristol group at Queen Mary University London, and this was a very controlled way of carrying out solvent annealing, which has been proposed in the emerging PV area for a number of years. The influence of solvent treatment is incredible. So again, surface scanning electron micrographs, where we see this significant increase in measured grain size and increase in what we anticipate to be crystallinity as a result of solvent exposure. Again, I'm just taking grain size as one measured parameter here, and we see this rather nice linear increase in grain size with increased solvent exposure. However, if we extract the device parameter performance metrics, then actually we can see that the 10-minute solvent treatment in every measured parameter, despite having larger grains, results in a lessened performance. Again, we compared this with solvent vapor annealing. So solvent vapor annealing is the classical emerging PV technique, where someone may take something like a heated substrate, a laboratory hot plate, deposit films on top with a small amount of solvent, and then cover those to allow a solvent vapor to be generated. And again, we look here just at the grain size data when we compare with solvent vapor annealing versus our controlled aerosol treatment, and despite the formation of much larger grains by solvent annealing, we can see that we have this really significant spread in grain size. The influence of that is really significant when we look at the reproducibility of our device data. So here, really the same data shown in two formats, so current voltage curves at the top for solvent vapor annealing, and we can see this lack of overlap of the films, which is showing large amounts of or rather large issues with reproducibility. And again, we can see when we look at the device performance metrics that not only do the aerosol treated cells typically outperform the solvent annealed cells, but we have this much tighter distribution, much greater reproducibility that's brought about by the aerosol treatment. One of the reasons for this, in addition to the increase in crystallinity, is the reduction in structural defects. So again, here, the microscopy are carried out by the Ducati group at University of Cambridge, and we can see the presence of a number of defects that are highlighted in the cross-sectional images, and here in the energy dispersive X-ray spectroscopy maps. We attribute these to being areas that are rich in lead, which we can see on the right hand side here disappear. They are eliminated during the aerosol treatment. So really the final aspect then is then thinking about the applicability of this. So we had shown fairly recently that it's possible to prepare devices of a variety of thickness. So for a number of applications, including photodetectors, we would like to have large thicknesses of films. So here we see films that are essentially sequentially deposited, and we see this polycrystalline stacked grain structure that exists through the film thickness. The reason I mention this is we have a limit in terms of the thickness of the films that can be processed, but we see this really quite nice improvement and this nice increase in performance as we increase film thicknesses that begins to tail off really quite rapidly, where we believe that the in-plane grain boundaries that exists are having a detrimental effect on film performance. In terms of PV, the desire to have thick films, particularly low light applications, is evidence here, where we see again really excellent device performance efficiencies at low light intensity. So again, classically, we've been measuring our devices under 1 sun of illumination. Here at a 10th of that magnitude, we see a significant sort of 5% increase in power conversion efficiency for the films that are thicker. So with the aerosol work, we demonstrated here that we can now produce really rather thick films. Okay, so here we're approaching about 1.5 microns in film thickness, and we can see really the remarkable differences at the thicker level between the as prepared films and those that have gone through the aerosol treatment, with a significant increase in performance across all of the aerosol treated cells, and again stabilized performance power conversion efficiencies here approaching 21% in the methyl ammonium lead iodide system. I show for completeness, these can be reviewed later, but essentially for every thickness and every device parameter, we see that the aerosol cells produce better. And really, in terms of highlighting the technique, to highlight this as a universal technique for perovskites and more, we show here our standard sort of research cell dimensions, relatively small area, and then we move up to a 1 square centimeter standard, where again in the inset here we see an increase in the power conversion efficiency from 16 to around 18%. When looking at the 1 centimeter cells. And again, just to bring this to a close and highlight the universality, we show a variety of device architectures that the technique is also widely applicable. So these devices are the so-called HTL-free cells. Here we look at one of these more state-of-the-art compositions. And again, we invert the device architecture here to look at an NIP structure, and in every case, the treatment has a positive impact. So to end, I'd say that I show that multi-step processing affords multi-level control. Microstructural control of defects in composition are important, really critical for improved devices. Additive engineering is something that is attractive, but I think we should be cautious about as we're adding to the complexity of already complex systems, and that the post-deposition treatment is something that really improves the performance of all perovskite systems and perhaps more. So I'll just end by acknowledging those that have participated in supporting the research funding, the all-important people that have carried out the research work, and to thank you kindly for your time, and I hope future questions. Thank you.